Alrighty folks, today the video is going to be about kinetic theory of gases. What kinetic theory of gases talks about is how you can use the kinetic theory of gases, the postulates of a kinetic theory of gases to compute the equations of ideal gases. While kinetic theory of gases is specially designed in our courses for ideal gases, but this is also valid for real gases, not all of the postulates that we're going to talk today, but 90% of the case or 85% of the postulates that we may end up talking about kinetic theory of gases for ideal gases is applicable for real gases as well. So the overall scenario of what we're going to do today is talk about postulates. Postulates are basically underlying assumptions that we need to consider in this chapter, especially to solve our numericals. What's happening? Well, might be a case where we might not consider some forces, which is applicable in real life scenario. So just trying to make sure that everything is sorted out in a way that it's simplified and the equations come up together. The neat equations come up together rather than being empirical equations, which can be applicable in solving problems. Postulates come from there. First, without any further ado, first postulate would be molecules of same gas are identical are identical in all respects. What that implies is molecules of same gas, say hydrogen or helium or nitrogen, it has same mass, shape, and size, which should make sense because molecules of same gases has to be same. Second postulate that is required to build the kinetic theory of gases itself, that is applicable in this scenario for the ideal gases, would be molecules are constantly in random motion, which is how molecules behave, but the assumption that comes with it is in along straight lines. This is something that we need to take into consideration, that molecules are constantly in random motion, but it is assumed that they're moving along straight lines. And if we know vector calc, then we can deduce the velocity with this simple equation. Oops. U of x, u of y, and u of z, where u would be ux I cap plus uy j cap plus uz k cap, which is the velocity of the molecule in all different directions. And it is assumed in this equation itself that ux is equals to uy is equals to uz, which means magnitude of this molecule moving in random direction would be uz squared, and its square would be again ux of square plus uy of square plus uz square. Now, since we know that velocity itself is constant, we can assume the further fact from equation 1 that 2 u would be equals to ux squared plus ux squared plus ux squared, which is excuse me, 3ux squared, which would be u is equals to root 3 of ux, which gives us the information that in this postulate, the body, the molecule is moving randomly along straight line in different directions, but their velocity in all directions are same. And if you have followed, or if you know about symmetrical velocities, then it means that the body is going to travel, or it's going to collide with each particles or other particles at 45 degrees of angle. Let's change the color and dive in postulate 3. I hope this color is good. The third postulate that needs to be considered is all the collisions of gas molecules among themselves and with the wall of container is elastic in motion. What elastic motion implies is simply since the body is having elastic collisions, which means collision between the bodies do not change the velocity of the body, and it holds elastic collision equations. What elastic in nature implies is elastic in nature would imply is the momentum and kinetic energy has no loss. Momentum and kinetic, what's the spelling of kinetic? K-I-N-E-T. No loss of energy. Why this is important is because when we assume for the fact that the collisions are elastic in nature, we are assuming the fact that there's no friction between these bodies, and when we strip away the friction component, then we can reduce the number of dependencies for these gases. And talking about those dependencies, the gases in that scenario, let me change the color, would depend on one or two intrinsic factors. The postulate that implies elastic collision would be the kinetic energy of the gas would only depend on the temperature of the gas, absolute temperature in that sense. Similarly, considering the fact we have considered elastic in nature motion, elastic in nature collisions, and kinetic energy of gas depending only on temperature, there is another thing that it implies is the volume of the gas is negligible, which is very important, I think, which is very, very important to take into consideration. What this implies in this postulate would be, if the volume of the gas is negligible, then when we are solving numericals, then we never consider volume of gas itself. What we would consider is volume of container. So to make a picture, it would look like if this is the container and this is the volume of if this is the container and this represent dots represent gases in the container, then volume of gas is negligible, would imply that we can compress the volume at this corner, and while we're solving the numerical itself, we're not considering this volume in the problem. Volume of gas not considered, but what we consider is the volume of the container itself. Which is counterintuitive and wrong in the sense that we're supposed to consider the volume, but hey, since we want to simplify the entire process, in ideal gases, in this scenario, we are supposed to consider volume of container itself, just the volume of container itself. Seventh point would be there is no intermolecular force of attraction among molecules, which is again completely wrong if you ask any physicist or some people who knows physics, because molecules are supposed to have intermolecular forces of attractions and they often interact with each other, right? However, we don't consider it in this scenario is because what we are interested in is intermolecular force of attraction or pressure of gas because of collision between gas and the container. That is, if this is our container, then we don't consider the intermolecular forces of attraction or pressure because of the collision between gases, ideal gases itself. What we consider is collision between the surface. Let me take another color. The surface and the gases, which is very, very important because these two assumptions, there is no intermolecular forces of attraction between gases, and collision between gases and container is what we consider is vital, because although in real scenario both of those things has to be taken into consideration, but when we start considering intermolecular forces of attraction between molecules itself, then we have to consider for the fact that volume of gas is not negligible, and the kinetic temperature of gases would not only depend on temperature, it would also depend on nature of gas, which is not the case in ideal gas scenario. So these are like the important postulates or assumptions that has to be taken into consideration if we are solving a ideal gas problem. In real gas problem, these number 6, oops, I think I didn't write number 6. Well, number 5 and number 7 is what makes the difference. Other side postulate that you might have to know is gases always tend to, oops, what happened? Gases always tend to expand in a container. Why? Because since the gases since the molecules are so small that gravity doesn't act upon it. So this is basically the entire, there are lots of postulates that we can talk about, but these are more or less the main postulates that needs to be considered. And what this would imply is our gases is independent of intermolecular forces between the other molecules, because there is no intermolecular forces of attraction, and we are not considering the fact. What we will consider is pressure of the container, the volume, pressure of the gas when colliding with the container, in the equation PV equals to nRT, which is the ideal gas equation. We will be considering with these postulates containers collision, containers volume, and temperature. When we heat the body, when we heat molecules, nothing else in ideal gases, which has to be crystal clear, because while we are solving numerical problems, most of the time we end up being confused with the wording that, hey, are we supposed to consider the pressure of the gases itself, there's container, and then volume of the gases, volume of the molecules too. But what we have to consider is based on the postulates, which is for the ideal gases, containers collision, which is pressure of the molecules with the container's volume, and temperature when we heat molecules, nothing else. So this is like the main postulates that needs to be taken care of. And in next video, what we will be discussing about how to deduce those equations.